Hello, my name is Jacquez Johnson, and this is Lab 2 Charge Tapes Revisited. Just to start off with an introduction and our models. The purpose of this lab is to model the charge on two charge tapes using GlowScript. It is a continuation from Lab 1, where now instead of assuming a single point charge, we're going to distribute that charge evenly across the length of the tape. And in this lab, we're going to be simulating interactions to balance gravitational and electrical forces, and we're going to be understanding charge distribution over a length using relevant formulas. So to quickly talk about the old formulas used, in lab one, we have gravitational force, which again is mg. In this case, we're going to be doing negative mg as it's going to be pointing down, pulling that piece of tape down. And for electrical field and force, things that we're already very aware of in this class. So new formulas that we were using in this lab specifically is superposition. To calculate the electric field across the shape, we're going to pick a piece. You're going to find your r direction, your r magnitude, your r hat. You're going to find the charge just for that piece. You're going to find the electric field just for that piece, and then add them up. And to get that charge per point, the total charge Q of the tape is divided equally among the n point charges, and we're going to see that in our code. So just to reiterate the experiment from lab 1 and some assumptions. So the result was 1.4 times 10 to the negative 8 coulomb for a single piece of tape acting as a point charge. The tape length was 20 centimeters, just some basic initial data. The system was that the charge tape and the charge tape and the charge tapes interacting. The surroundings were the table, books, Earth's gravity, things like that. And our computational model required these assumptions: one, ignoring air resistance, and two, that the charge is evenly distributed along the length of the tape, which we know in reality it may vary due to irregularities and things like that. So a quick preview. So the coding resulted in the electric force being 4.82 times 10 to the negative fourth. And unfortunately, the code did not cancel out the gravitational force, but we're going to figure out why, and we're going to find the correct Q value moving forward. So we're going to do that by taking a look at our code. So now to talk about my code, just starting at top, we have our constants that we set for K and G. Looking into the mass, we just divided by 1,000 to convert it from grams to kilograms. Q we're going to pull from lab 1, which I then edited to get 2.825 to get that correct number. But just starting at top, we're going to have our E field function that we defined earlier from lab 0. We're going to use that to just quickly calculate E fields instead of having to manually do it. Then we have the given line charge formula, which is going to calculate, the magnitude of each point charge, the mass of each point charge, and then we're going to make different point charges so we can add them all up. Moving forward, we're going to set the top tape at 0.00 or 0.03 meters above the bottom tape, which is what we found in our experiment. E scale, we're going to set that. We're going to set our FE scale as well. And to calculate the E field at the location of the top due to the bottom, we're going to calculate the E field of the bottom on the top. And then we're going to calculate the electrical force on the top due to the bottom. And we're going to do that by multiplying, F equals Q times E. And then we're going to create the arrows for the necessary fields so we can represent it. And then at the bottom, we're going to calculate our gravitational force, which is just M times G. And we're going to get this result right here, where we see that the magnitudes are equal and opposite, so they cancel out. And we see all the different charges and direction of the force. Thank you. Now that we've taken a look at our code, let's go into the findings and conclusion. So in our findings, we see that just graphically before that the gravitational force is much stronger. This could be because my initial calculation of Q from lab 1 was incorrect, causing the whole strip to be less than the force of gravity. So after finding the correct value, we get the correct and equal Q to our left in the bottom left model. We see that they're both equal and opposite. So after we get a magnitude of 1.96, which matches the magnitude of the gravitational force, and that correct charge was 2.825 times 10 to the negative 8, which was almost double. So some potential errors would just be numerical approximation errors. So breaking the tape into smaller segments may introduce errors. Measurement errors such as incorrect setup of initial positions or conditions, such as the distance calculated between the tapes. So what if you had to model each of your tapes as a single point charge, like in the previous lab? So we would get the incorrect electrical force because it does not account for real life scenarios. So line charge was 2.825 times 10 to the negative 8, and point charge was 1.4 times 10 to the negative 8. And why do these estimates differ? It's because in lab 1 we treat it as a single point charge, but in lab 2 we're going to use superposition, and also all those different evenly distributed charges have different R values. So therefore, that's going to give us a different result. And lab 2 would be closer to reality as charges are dispersed on an item evenly, not just located at a single point. Thank you.